So yeah, I'm Erik. I work in the GC group at Oracle, and today I'm going to talk about automatic heap sizing in ZGC, which is something I've been experimenting with recently. So I always like starting off by talking about the goals of our projects, and what we want to achieve with ZGC is low-level latencies, like sub-millisecond pause times. We also enjoy our scalability to large terabyte-sized heaps, and we also really focus on making user configuration as little as possible. So auto-tuning as much as possible. So looking at what we have today, we have a concurrent moving garbage collector, and its generational has all this low latency. We have reached a good CPU versus memory trade-off with generational ZGC, and it scales to very large heaps, and the configuration is mostly automatic. So in my opinion, it's pretty awesome. Looking at the automatic configuration aspect, there's plenty of stuff going on here. So first off, we have the concurrent GC threads. This is one of these things where if you have too many concurrent GC threads, you might start preempting the application a lot, and it might cause latency issues. Whereas if you have too few concurrent GC threads, it could be that you get an allocation stall, and you have another type of latency situation going on. So it's really important that this is right. So we end up doing automatic tune and figuring out what this should be automatically, and even reconfiguring the system at runtime when we realize that the situations are changing. So the next thing is generation sizing. This is also one of these things where it's really hard for a user to reason about how large a young generation should be compared to an old generation. But whatever you choose, it might have large impacts on the performance of the system. So we have a bunch of cost modeling and figure this out automatically. Next thing is tenuring threshold. This denotes how many young collections we run before we promote objects to the old generation. This is also quite tricky for users to figure out on their own. So we do a whole bunch of stuff to figure this out automatically. And similarly, when do you start collecting the old generation? Might be tempting to have a flag where you set a threshold and let the user deal with it. But instead, we do a bunch of cost modeling, do automatic tuning, figure this out automatically. So there's a whole bunch of automatic stuff going on here to reduce the amount of configuration surface to the user. So what we tell people is all you need to do is to set the heap size, and then we'll figure out the rest on our own. And that should be a pretty reasonable thing to do, right? What could possibly go wrong? Yeah, there's a lot to say here. So before talking more about that, I'd like to take you back to my childhood and talk about, I think we do things based on where we've been before. And I would like to explain a bit why I'm here today. So something I don't tell a lot of people is that I grew up in a Mac OS 7 cult. And so back then, you had to configure each application how much memory it needs. And this was my favorite game, Escape Velocity. And here we can see you have to configure the amount of memory. If you got it wrong, you get an error telling you that, yeah, here's a crash, you can't run the program. So then you have to ask yourself, how much memory does a space game need? And this is pretty hard to tell, really, and was quite traumatic to deal with. So we can configure this application to run with 8,300 kilobytes, as it turns out. But then you have to wonder, will it continue to run or just start? It was quite messy. So later on, when I grew up, I left this cult, and it felt great. Nobody else was doing this, and yeah, it was a pretty good time. But then later on, we started using Java. It really felt like I go back to this cult again, that you had to specify these heap size parameters. And yeah, I don't think it's good enough to say all you need to do is configure the heap size. We need to do better than that. And so how do you configure the heap size? How do you do it? Well, there are different methods for doing this in practice. And the default is to use 25% of the available memory, or truncate to the compressed OOPS limit around 32 gigabytes, even though with ZGC we don't really use compressed OOPS, but this is how the heuristics work. But I think the question we are asking might be wrong. We're asking how much memory does a program need? It's sort of like asking how long will a program take to execute? The halting problem is kind of hard to answer that question. So if you do this manually, you might end up looking at two different sides of the spectrum. On the one hand side, you want the heap to be large enough for your problems to stop. And the problems are latency problems and the throughput problems, and they might look different in different applications. But looking at the latency aspect, you want to avoid allocation stalls. So you want the heap to be large enough that you don't get allocation stalls. But even then, there might be spikes in the workload and various things where you need to increase the amount of heap anyway to deal with other phases or whatever. But then this also has an impact or interaction with the concurrent GC threads, that if we start having too many concurrent GC threads because the heap isn't large enough, then that might have a latency impact as well, because we start preempting the application a lot. So we want to make it large enough that we don't need so many concurrent GC threads. And the performance improvement by increasing the heap size also has diminishing returns. So you get to a point where you can make it larger, but it won't really change the situation that noticeably. Other than that, we also have barrier storms. So if you have too high frequency of GC, it might be that you're running into a lot of barrier slow paths, and it might be not ideal for the application. So that was all on the side of trying to make it large enough. But then you have constraints that you don't want to set a heap size that's too large, because then you might skate off the boundaries of your machine limits, and you will, the OS will kill the application. So because of that, you have to make it small enough that you won't run into this problem. And then you have to deal with what the neighboring processes are. If you have some of those, you need to make sure that there's enough memory for neighboring processes if you have them. With containers, you typically don't, but otherwise you do. And other than that, you might have file system caches you don't want to discard, and there might be a whole bunch of native memory in the JVM as well. It's hard to figure out how you should set a heap size to ensure that we have enough native memory. So one approach for setting a heap size is to manually increase the heap size from some random number. So in this example, we start off with a small heap, get out of memory. So clearly we need it to be larger than that. We double it, still get out of memory, so we need it to be larger than that. We double again, now we're getting allocation stalls, but it's at least not throwing out of memory exception. So that's probably a good indicator we're in the, going the right path here, but it might be that we need to make it larger again. So we double again, and we get into a situation where we have less latency problems, but it still runs slowly because the overhead of doing GC might still be too large. We have lots of cores in the system, and we just simply need more memory overhead. So we double again and eventually get to a state where it seems fine. Until, of course, you run for 2 weeks and get some kind of native fragmentation error and end up having to crash anyway. So that leads us to the other side of the spectrum, which is to make sure you're not using a large enough not too large heap. So the other way of looking at it is saying, oh, I know how large my machine is. I bought a 32 gigabyte machine. So let's use most of the memory for some definition of most. So how much is most of the memory? Well, maybe we can calculate that. So we want to have some kind of critical reserve available in the machine. Otherwise, the system will degrade and it will perform terribly. So let's have that. Then we want to have some amount of memory for file caches. And now we found how much memory we can use for the JVM. Now, we need to account for the native memory as well to find a heap size. So how much native memory do we use? Well, we have to think about what is the maximum amount of metaspace we're using. And I mean maximum, so not, all of these native memories need to be the maximum. We have a code cache. You need to have enough memory for the maximum amount of memory the code cache uses. We have a malloc heap. How much will that use? We'll have to consider that. And how much fragmentation will that induce after running for 2 weeks? And then how much GC metadata do we need? And it's very implementation dependent. Then you have direct map byte buffers. How many of those are you using and how much memory are they consuming? You have to think about that. And in the end, the thread stacks also consume native memory. So you have to think about how many threads you're using and sort of figure out how much native memory you need for that. So great success. We've reverse engineered the JVM, and now we can figure out what a heap. Yes, Latimer? Oh, there was the code cache. Right. So reverse engineering the entire system is tricky. So once we have discovered what the maximum heap size is, we might not want to get too close to that max heap size because when we get allocation solved, no problem. We have a soft max heap size option that allows you to create a bit of extra headroom here for the GC algorithm. And that typically works out fine, but it's quite hard to configure this. But then when you start running, it might be that you have a workload that is running at a kind of creeping allocation rate when the load is low. And even though you've tried really hard to configure this right, it might be that the memory is creeping up, but the allocation rate is low, so we don't really start a garbage collection cycle because you said we have all this memory you should use. And then the load changes and maybe the residency changes slightly and you end up with an allocation stall anyway. And now when you look around in the system, you see that there's unused memory there because in the end, we didn't use the sum of all the maximum native memory. In practice, we used less than that. So there is actually a bunch of memory available on the machine, but we've artificially constrained ourselves to say, no, this is the maximum, we get an allocation stall. So I think this is quite problematic. So I'm hoping that we can say goodbye to these options. You don't have to. So you can still set heap sizes the way you'll love to do it if you want to. But the hope is that if you don't, it will be totally fine. So the way this works is that we're defining some sort of GC forces. Let's call it the weak force and the strong GC force. And this has to do with these two different sides of the spectrum, that the weak GC force wants to make the heap large enough to run smoothly, whereas the strong GC force is constraining the system to fit within the machine and not skate off the limits. Starting with the weak GC force, we talked about the defaults. How much memory should we use by default? Hard question to ask, or to answer anyway. Very easy to ask, in fact. What we're doing here is to change the question. Instead, we're asking the question, what trade-off between memory and CPU is acceptable for running well? And Well, it's hard to predict exactly. It's a lot easier to be in the right ballpark. And now I have a JVM flag here with a value of 5. What does this mean? Hopefully you won't have to know. So this flag describes how aggressively we're going to GC on an abstract level. And hopefully you won't have to change it, but it's there if you need to. So the first thing we're going to do, we start off with a 16 megabyte heap, which is quite optimistic. If you run Java-version, you're going to find that you use 45 megabyte of RSS, so on the minimum heap. So it's a very small heap size. And then from that, we want to grow the heap until we hit some form of diminishing returns. And we want to make sure that we fit in the live set, don't get allocation stalls. We want good throughput, and we also want to have a good balance of machine resources. The first thing we're going to do is to establish some kind of initial ballpark boundaries for where to search for the right heap size. And then after that, we have a control system that incrementally finds the right break-even point. Since ZGC is concurrent, we can also utilize the very fact that it's concurrent to make things a bit smoother in the beginning, because we're starting off with a very optimistic heap size of 16 megabytes. So we will very likely find that we need way more memory than that, like orders of magnitude more. And so when we start a GC, we're never going to stop because of GC. It continues running. So it might be that while we're running a garbage collection cycle, the application allocates a whole bunch of more memory, and we're just going to give it to them. And at the end of the GC cycle, we're going to say that you probably needed at least as much memory as you have after the GC cycle finishes. And this way, the heap size that we're computing is more like a softmax heap size, in that it's an indication of this is how large we think the heap should be, but we're not going to hold back if you need more allocation stalls. So now that we have some lower boundary, we can also infer a little bit from just looking at the allocation rate. As it turns out, you don't want a very high GC frequency, regardless of the CPU overhead of running the garbage collector. If the frequency of garbage collection is too high, then we're running into all sorts of problems from the application thread, such as global synchronization, save points, various storms, concurrent stack scanning, processing, and compiled method entry barriers and things like that. So you want to space the GC cycles a little bit. And by just looking at the allocation rate, we can infer some sort of minimum heap size for the system, which is useful for growing very rapidly in the beginning. Once we've done that, we perform incremental tuning of the system with a control system. And we establish a target GC overhead that we want based on this GC pressure. And we measure the actual CPU time spent by the GC and CPU time spent by the process. And we can calculate how much CPU overhead we have. Now, in this system, the major collections collect both the young and old generations. It has a complete picture of the total cost of garbage collection. And that allows major collections to both grow and shrink. Minor collections, however, have a limited view of reality, where it doesn't understand the cost of all collections, but it's good enough for growing the heap, because the cost of young collection is going to be at least the amount of GC overhead of the entire system. So it allows us to still grow the heap in young collections. Now that we can establish GC CPU overhead of the system, we can compare to the desired one and calculate some kind of error signals based on the discrepancy. And we feed these error signals through a sigmoid function, which smoothens things out so we don't get extreme increments or decrements. You get some reasonably small increments and decrements. And in the beginning, first couple of seconds, we're a little bit less conservative. This is really good at converging at a particular target heap size. But in the beginning, we don't really think we're going to converge anyway. So we perform a bit more aggressive increments. Now, as you can imagine, resizing the heap involves resizing the generations, the young and old generations. And this is one of these things where we have a bit of a luxury situation with generational ZGC, partially because there is no latency impact of having a larger young generation or having a larger old generation. So we can remove latency from the trade-offs and focus only on CPU overhead. And in ZGC, we also don't have a notion of capacity for our generations. So is a little bit more fluid. So finding the right distribution of the generation is already something that we do automatically. So given a particular heap size, we will try and self-balance the system so that we get the distribution of residency in the generations that yields the lowest CPU overhead, which is what we're trying to optimize. So that was the weak GC force. And then we have the strong GC force where you say that enough is enough. Let's not use more memory than we have on the machine. So as I mentioned, one of the things we need to do is also look out for neighbors here. I don't know if you usually use a radar for looking at your neighbors, but you don't want to collide with them. And we also want to uncommit memory when the memory is depleting. So we're actually monitoring how much memory is left on the system and act accordingly. But the uncommitting itself might also have echo effects where we uncommit memory and then, that leads us to think we can use more memory and then it goes back and forth. But we have a control system that keeps this pretty stable. And the way we do this is to define something I call memory pressure. So we have 3 different levels of pressure on the system by looking at how much memory is left on the machine. And once we computed the memory pressure, we can scale the GC pressure by the memory pressure. And by doing that, we're essentially moving the convergence point for the heap sizing algorithm. And another benefit of this is that all the JVMs running concurrently have a shared view of what the memory pressure is. This allows them to coordinate actions with each other without having a global coordinator. Instead, they will all see that the pressure has increased and they will all pay their share of extra GC tax to get the heap size down. And in ZGC, we also have separate uncommitting from the GC cycles. They're orthogonal. We have a separate thread that uncommits memory. And it has a delay for when to uncommit memory. This delay is also scaled by this memory pressure. And the effect of that is that as you run lower and lower memory on the machine, we start more and more aggressively uncommitting memory. So when you get to the extreme side, we're running out of memory on the machine, it will uncommit memory very aggressively, very quickly. So I talked about 3 different levels of pressure. The first one is what I call concerning. So we get to a point, and these numbers are just what I'm prototyping with it now. So if you have any feedback on what these numbers should be, I'm more than happy to listen to that. But at the moment, it's 20%. So when you have 20% left on the machine, we say that this looks a bit concerning. Maybe we shouldn't model memory as free anymore. And this is a point where we're starting to have lower margins for getting allocation stalls. And we also might start interacting poorly with file system caches and things like that. So at this point, we linearly increase the memory pressure with how much memory is left. Run into some interesting interaction with Mac OS and Windows, where it turns out on Mac OS that there is a system that compresses memory, sort of like swapping, and this interacted quite poorly with this, because it's one of these situations where the assumption that a larger heap is going to perform better isn't always true. Because with a garbage collected system, when you start compressing memory, the garbage collector walking through all of this memory needs to decompress all of this memory, which makes GC more expensive. And the algorithm says, oh, GC is expensive. Do you know how we solve that? We increase the heap size. And the OS starts aggressively compressing all of this garbage that we didn't really need instead of just collecting the garbage. So it kind of causes weird cycle where the heap just explodes and you get terrible GC latency, and it didn't work very well. So fortunately, we were able to model this in the cost modeling by looking at the compression ratio and looking at making that part of the memory pressure. So as the amount of memory that's compressed increases, we start being more careful to increase the heap. And that made the cost modeling a little bit more complicated. But on the other hand, when you think about it, how can users reason about this? I don't think they can. So we have a high threshold where the pressure is high. That's currently when it's 8% left on the machine. At this point, I think we start getting a bit more alarmed that this is really starting to look bad and start exponentially increasing the memory pressure. This will quite quickly lead to back-to-back GC with as much power as we can throw at the problem. And the margins here are starting to look pretty small. The last level is critical. So when there's 5% left on the machine, this is the point where we'll start having hard limits that you're not allowed to use anymore. You get allocation stalls, and if you can't resolve the situation, you get an out-of-memory error. But it still has enough memory that we can handle throwing the exception. So other than that, we also monitor the CPU utilization and scale the GC pressure according to that. If you think about it, if you have an application that's using a very small amount of CPU, you might not want it to use an extortionate amount of memory. So if we can pay a little bit CPU to get the memory down, we probably want to do that. And the opposite is also true, that if you have an application that's using most of the CPU resources, you might want to bloat the memory more to try and do what you can to reduce the amount of CPU if memory is still available. So we compare the ratio of CPU usage and memory usage and scale the GC pressure accordingly. So I talked a bunch of nonsense now about the policies and what they do. So I think it's useful to have a look at some of the examples of what this actually buys us. So we had the example from earlier where we got an allocation stall, but there's still some memory left on the machine. How would this pan out with automatic heap sizing? Well, first of all, if you have a low allocation rate that's creeping up, it would have a much smaller heap size in the first place. So there's currently a lot of headroom here for dealing with bursts. Even then, if you have a situation where you have an ongoing allocation rate that's higher, it's still the case where we're able to use more of the machine memory, because we can recognize that although the maximum amount of native memory might have been some number, if we're not actually there, we are able to use the unused memory on the machine to deal with allocation stalls. And we can even start digging away at file caches temporarily to avoid an allocation stall. So another situation is unexpected native memory usage. So in this situation, we have a manually heap-sized system, and when you suddenly start allocating some extra direct map byte buffers, it might be that, oh, we run out of memory, which is unfortunate. But with automatic heap sizing, we'll instead recognize that, oh, you start using more native memory, then I guess we need to shrink the heap and accommodate the extra native memory. Another example is how to deal with neighbors. And with manual heap sizing, if there's an extra JVM that needs to run, it might not be able to, because we don't accommodate them at all. But with automatic heap sizing, since we are monitoring the system and acting accordingly, we can respect our neighbors in the sense that we allow them to run side by side. But I think we can also do better, similar to how with real neighbors, if you are baking and you run out of flour, you can knock on their door if you behave well and ask, could I please have some flour? And that's exactly what we can do here, is that if one of these JVM suddenly needs more memory, that will increase the memory pressure in the system, and the JVM that has more memory available is able to uncommit memory and give it to its neighbor. So another thing that touches on this is heap priming and pre-touching. This is one of these situations where currently you have to choose between throwing startup or warm-up under the bus. And the question is, which one do you throw under the bus? It is not easy to say. So if you want a good warm-up performance, you can set XMS and XMX the same. Then we'll commit all of the memory up front. And if you set always pre-touch, we'll also map in all the memory. So this makes warm-up smooth, but it does have a startup cost. However, if you want good startup performance, you can set XMS smaller than XMX, and then we will not commit everything during bootstrapping. And you can disable always pre-touch. We will not pre-page in any memory. And this is good for startup, but it comes with a warm-up overhead instead. And I'm all about having the cake and eating it too. So what we're doing here to solve this, because if we don't do anything, we start with 16 megabytes of memory. It would appear that we get good startup, but have to pay a cost of warm-up. We don't want to do that. So instead we have concurrent heap priming. This works a little bit like curling in the sense that we're warming up memory that's ahead of the application threads and making sure that it's committed and paged in. And this way we can start with a very small heap size and ensure that whenever the application is allocating memory, we're a few steps ahead of heating up memory. So it's going to be very nice. Okay, so let's have a look at evaluation of this. So what I've done here is to run SpecJBB 2015 on a 16-core machine with 256 gigabytes of memory. And in this graph, we have capacity, heap capacity being shown in the red, CPU usage shown in the yellow, and GC CPU usage in the blue. For anyone that's run SpecJBB 2015 before, there's a warm-up phase first where it's trying to find the highest injection rate we can manage. And as you can see, the CPU usage of the application is going up and down quite a lot early on, and then it starts linearly increasing. And when it does, we're increasing the heap size. So you end up with some heap size around 60 gigabytes in this case. After that, we find that, yeah, we could keep increasing, but maybe that's not going to help you all that much. Now, what happens if you constrain the system to 32 gigabytes instead is that the point where it converges is now around 25 gigabytes instead of 60 gigabytes, because it starts seeing this memory pressure and that, well, maybe we shouldn't keep increasing because we're going to run into trouble. And as you can see, when you do that, the GC CPU usage maxes out at the end at 25% of the machine, which is where we stop. So it's all interesting what happens when you run at a maximum load, but in production you're probably not going to do that. So it's interesting to look at what happens if you manually specify the injection rate to something lower, where the machine isn't begging to get killed. And here we have a 5,000 injection rate and 5,000 per second injection rate. And what you can see here is that we're converging the heap size around, was it 12 gigabytes, something like that. It turns out we don't need really more memory than that, and the GC CPU usage is kept relatively low, the blue at the bottom. If we increase the injection rate to twice that, we start recognizing that we're starting to use a considerable amount of the CPU resources. So we should probably try and increase the heap even further and increase the capacity something higher. And when you get to 15,000, we get an even larger heap size. Now, what happens when you have a benchmark salad is the question. What I'm running here is a bunch of different programs at the same time. So I have SpecJBB 2015 running with a 15K injection rate on this 32 gigabyte machine. Then I have an H2 database application that's running alongside with that, and a Cassandra instance as well. So in the beginning, we start SpecJBB 2015, and it starts increasing the amount of memory. Then I start the database application. It starts increasing memory, and we have a bit of a surge of liveness in this database application in the beginning, in the early initialization phase. And this is exactly one of these situations that I talked about, when we can go to our neighbor and ask for a bit of flour. And it turns out that SpecJBB 2015 is able to deliver that flour and give memory back to the database application so it can satisfy its applications. I don't know if the metaphor, I don't know if it holds in the end, but you get to a point where it hands the flour back, and I don't know if you want recycled flour, but anyway, we have this Cassandra application that we're starting as well. It has a smaller amount of heap memory, but it has a bunch of native memory as well. And you get to a point here where the H2 application stops, and you can see then that SpecJBB 2015 starts increasing its heap size because there's more memory available on the machine. And eventually the Cassandra application stops as well, and the SpecJBB 2015 instance is able to recover to its normal operation. And you see that you get back to that 25 gigabyte mark that we had before. So that was all I had. So do we have any questions?
Hello. Do you have any plan to allow that the weak GC force and the strong GC force to be directly specified by the user? Like, for example, if we are running a custom environment that, like if you are looking at the standard container size that may not work in our environment, then we need to tell you what is the actual strong GC force in that case.
Currently, it's not configured. You mean the threshold levels where they go?
Just like how much, what is the exact maximum container limit? Like you cannot tell using the JVM the current approach because we are not using the standard container.
You can't free the memory?
No, you can free the memory size. You can reduce the memory size.
Oh, we definitely do. The JVM keeps track of what the container limits are. So, and that's something.
Right. So we sometimes sometimes, for example, our container limit isn't a fixed value. So maybe our container limit can grow when your application are still running. That's possible.
So let's put it this way. I think we had some discussions about how the JVM might not really be fully capable of dealing with that. This algorithm is, though, it's continuously monitoring changes to the container size. And if it does change the size, it will act accordingly to resize. But I'm not sure if the rest of the JVM is capable of dealing with that situation.
Sorry, just one question just about native memory. So my own local VM may be allocating memory through direct buffers or through foreign memory API. My neighbors may be accessing or allocating native memory. I didn't quite get on your slide whether the control system knew about the local native memory, or was it only just because it was actually sampling the overall native memory?
So it's not sampling the native memory, but it is sampling the amount of memory available on the machine, and hence it's implicitly sampling the native memory usage. If you start using more native memory, you're going to find that you have less memory available on the machine. And we will act accordingly and start reducing the size of the heap to make sure that we have enough margins in the machine. And that way, it will have the implicit effect that when you start allocating more native memory, and we don't know the source, it might be in our JVM, it might be a different JVM, we'll be able to shrink the heap size and deal with it.
About file system caches, how do you model, how do you weigh the usefulness of retaining file system caches versus the usefulness of expanding the heap?
I have no idea. So yeah, I've selected the 20. The thing is that there are multiple reasons for having headrooms. File system caches is nice if we can have, but we also, I talked about how earlier on we have heap headroom inside of the heap. So if you specify a max heap size, we try to not get close to it because it might incur an allocation. So that headroom we can now put outside of the heap instead. And that can overlap with file system caches. So instead of grabbing a bunch of memory that could be file system caches, we can let that be file system caches instead. And only when we're missing with the heuristics and something unexpected happen, we can grab that memory if we need to avoid an allocation stall, which is something we're not capable of doing today.
Thank you very much. Great work.
Thanks.
Yeah, simple question. What's the status and plans for this work?
I will ship it tomorrow. No, I have a prototype and it's running pretty well, but I think there's a road ahead of performing evaluation and seeing. The thing is, it needs to deal with very interesting situations, and I have a setup with a whole bunch of different strange things, like running 200 JVMs in the same system and see what happens. And I think it's running pretty well, but by pretty well, I mean that it's not crashing, but it's running horribly if you don't run 200 JVMs in the same system. But yeah, there's evaluation to be had and reach more confidence that the random numbers we have are what we want them to be, etc. But otherwise, it's working fine.
So in terms of the scenarios that you've been experimenting with, one interesting scenario, which I assume you've probably dealt with, is you have a bunch of different applications running on the same box, and all of them are subject to some oscillations in their workloads and so on and so forth. Have you compared something where you give each a certain specific part of the JVM, of the memory, kind of put them in their own containers versus letting them all flex in the manner that your algorithm allows you to do? And in that case, how do you actually even assess the goodness of the overall result? Because in some sense, one of the applications might run better for a little while, the other might run better for another while, because your system is always adapting. How do you even evaluate something like this for, this is working well?
That's a great question. And that's it. I have a bit of a setup where I'm evaluating all sorts of interesting situations. And one of them is looking at benchmark results and see how they perform compared to a more tuned system in these kind of situations. But yeah, it is definitely difficult to assess. And when it comes to, so if you had a global system that could tell you should have this heap size, compared to that, it's a bit more like having a bucket that you fill up with balloons. The way it's modeled in terms of forces is more that they will eventually get to an equilibrium state where they're paying equal tax, so that all the applications are being punished. It's not just one of them that takes the whole, becomes the scapegoat that has to shrink its heap while the other ones are continuing as if nothing happened. Since they all have a shared view of what the memory pressure is, they all take equal action, and that way they have a shared impact on their corresponding GC CPU overhead they try to reach. So in that sense, it really is like having a bunch of different size balloons in a bucket, and if you make the bucket smaller, then they will all kind of try and squeeze together somehow. It doesn't happen instantaneously, but it happens fairly quickly.
So early on, you showed this intriguing option about GC pressure, and its value is 5.
Yes.
And then you explained your algorithm.
Yes.
So having teased us about the option and saying the value is 5 and you shouldn't need to think about it, can you now say more about, well, what are the units and what's the range of that value, or should we just not think about it and leave it at 5?
That's a great question. So I think Andrew Haley over there had the idea, I think it was a couple of years back, sent a suggestion to the ZGC mailing list that maybe we should have something like the compiler O option, that O3 is probably optimizing harder and something like that. It's more that kind of thing where I don't really want to specify exactly what it means, because by specifying it, I think we will lock ourselves into a situation where we can no longer improve the heuristics, because we've said that, we're going to have this GC or CPU overhead, and suddenly we found out we can do better than that by looking at context information and find that actually that's an inappropriate value now. So I want to think of it more like higher means it's going to GC more, less means it's going to GC less. But exactly how much is, at least as of now, undefined, and something that might change from release to release. Although the hope is that you won't have to mess with it at all. But we'll see about that in more real-world situations. All right. Thank you, everyone.